me maybe say what the goal is now in the middle of the talk. So what we've already sort of seen is that.
Could you break the chalk?
So those guys correspond to Bivector fields. So what I will have is I'll have some guy here, and I want to promote this to some differential.
So this pi is not the pi that we...
No. And I want to promote that to a second order differential operator that still has this guy as a symbol. And the construction that I want to do is that you just plug it into one vector, and then I want to take the divergence of that vector field with respect to some volume form. So in particular, I want to understand, yeah, that's why we sort of need to understand what are those differential operators or like one-shots. And the next thing will be that we want to understand these volume forms. Let me just say what, like, this will be like some differential operator, and in particular what this, like the type of object that this thing is. We have two forms, we can just plug this guy in and we'll get functions. And those two forms, they will appear actually not really as two forms, but as tensor product of one forms. And I want to construct these guys. And now, sort of like in this non-commutative world, what I will need to do is have such a guy that happens to be sort of a pi morphism, then I want to find these guys. And so like the way how this construction actually works is that I sort of can do this in two steps. I can first, and so now you just think one forms, so I can first promote one leg to a vector field. And this will also work for the jet bundles. Here I can evaluate one forms against vector fields. Even though that is the goal where I want to learn that up with, it would sort of be enough to understand such a thing. Such a lift. The claim is we can construct such a lift if we know what a volume form is. I mean, that's sort of how this divergence, what the divergence is. Maybe that's it. This guy, a map like this, so this is a non-commutative divergence, and that's what we want to find. Let's maybe recall how can one construct this divergence in the commutative world. So in normal the differential geometry, what one can do is let's say we have trivialized the tension bundle, or this, like what Cartan's moving frame, and we can say the divergence of a vector field that's given by a formula like that. So sort of the goal would be to make sense of this formula. And since we've already had a couple of long formulas, let me just say, not give exactly what all the formulas are, but just sort of what type the objects are. But yeah, sometimes I only need to say how to make sense of this Lx. Maybe not write down what the full formula is, just like there is a way how to, or there is a sort of lengthy formula for how you'll have to take Lie derivatives of one forms, and then using this we can just do exactly the same construction in this non-commutative world. There's a big of those normal moving frame, or if you have one of a trivialization of the augmentation ideal, this will give us also a moving frame on the representation variety. You know, that's not an unreasonable thing to do. And the claim is sort of using this formula in the correct way, we can define the divergence map basically by the same formula. They one needs to sort of like shuffle the factors around in the appropriate way. Or maybe I should say, so from this gives me a basis alpha I of this and xi. The base of vectors and covectors. And I can just pair those. Trace. There's again this kind of pairing formula that will give us such a divergence. I said here that. So in particular, this formula will give us that diagonal arrow. But then we can sort of ask how much does it actually depend on that moving frame. And in the commutative world, it's not supposed to depend on. It's only supposed to depend on the volume form that didn't use this. How it will actually change if you change the moving frame. exchange it by some invertible matrix in this with values in k pi. And then form formula. Values is just x evaluated on the following type of one form. That's sort of like from the formula will work in the same way that makes it such that on commutators of elements here, it will be 0. As in particular, we can use this now to define our non-commutative volume form.
So the right-hand side, what is its nature? Is it a number or what is it? Like the difference of two divergences, this x applied to the trace is what?
So like from this picture. But we already know what it, like we have a map from here to here and we know what it is from here to here. So the difference will be, a map from like these non-commutative vector fields into I. Or similarly it's given by, put this on the other side and it has to be given by non-commutative one form, and the claim is that that's that one form. So like one motivation would be like if you want to understand the determinant line of the vector space, you could just as well say it's an isomorphism where we mod out SLN. So we'll just do exactly the same thing. At least that would be sort of our first attempt. And if you plug this into the formula, it will still, everything will work and it will not see that difference. And we can actually do a bit more because I just look at what this formula does. If we had our matrix and we extended it by one more, then the formula doesn't see this difference. So in particular, we could also, like if you have two of those isomorphisms and they sort of become the same, after you enlarge, or like after you add trivial bonds on left and right hand side, the formula exactly stays the same. Then sort of like what's more obvious, so this thing is a torsor over and that guy already has a name in the literature. So that's K1 of K pi.
Do you know how it looks like?
Yeah, it will be the next. That's weird. This is sort of one, or like this is maybe the first time where like this restriction to free groups is really seriously used. So this thing one can compute. And Starlings did this in the 60s. It turns out, so all these matrices, if you consider them up to conjugate, like up to commutators, then you can always bring them to like ones everywhere, and here some element of our group. So in particular, like this is surprisingly small.
This Abelianization, what is just a billion group with n generators, or what is?
Yeah. Oh yeah. Let me skip to where things are maybe a little bit interesting again. So you just sort of say what are the ingredients. So we said if we start with something in we have something in this guy, and we have our non-commutative volume form. Then what we can produce is sort of this divergence map, and then lift that guy to the second order operator. Yeah, let me say what these things. So like everything that we did is just some kind of group homology. Maybe let's recall. Right, the starting point was this short exact sequence, and then we did something to that guy. But in particular, like this two-term sequence is a resolution of that thing. So whenever we want to compute group homology, we can just take those things. And because I made my life a little bit easier, we can start to find what is reduced group homology. Or in general, one can, whenever we have two groups, we can define what is a group homology. So this thing with whatever some coefficients. Then here we'd have to take a resolution of the first guy and the second guy that are compatible. So let me just do this homology of some kind of group chains. But then we can take the cone over that thing and take the homology of that. And in particular, we can always take, so for instance, the group homology of our group relative to the trivial group. And what this does for us is it just kills that guy. So for instance, yeah. So then that guy would now just be first reduced group homology of our group with that coefficient. And so where these kind of weird extension triangles, where they come from now. Where they may just, so we can also do the same thing with sort of reduced group homology of a product of groups. Then we can identify whatever this thing was, now it gets the new name. And at some point we want to do something real, or like we want to mix of this pi and pi representations. Now if I wanted to compute this relative group homology, I would have to take like a resolution of pi and a resolution of pi that are compatible. And it turns out like the following. Or you can always sort of take the same resolution. So for instance, that guy is a resolution of k in pi. So in particular, I could just take the same as a resolution of k is a pi module with the diagonal action. But one can sort of like kill one of those factors here. If I wanted to compute any of those, like to compute some kind of group homology, like this, I'll need a resolution like that. And now sort of like one thing where I made my life easier, like I made everything reduced in such a way that you can kill everything here, and you'll just end up with that triangle that we've been looking at before anyways. So let me say what the upshot of this is. I have something. I have something in here that for some reason or another I call the Bivector field. And my goal was to sort of lift using this triangle. And what this amounts to is just lifting whatever that element is to here. And I sort of gave one procedure that uses the sort of non-commutative volume forms. How you can find such a lift. So let me give some other, like another way how you can arise geometrically at this thing. This is like where all those three groups actually come from, or where motivate. So the original motivation were surfaces. But if you have a surface, a boundary, then the fundamental group is a free group. And so in particular, or let me also make some more choices. Let's maybe also choose a couple of discrete points on some of the boundary components. Maybe not all of them, but it doesn't matter. And so if I take a surface like that, and we draw a surface, and maybe some points So let me just collapse all the points to one point. So if I have just single point, then I don't do anything. So this will be the free group that I'm actually interested in. So then let me tell you where this, so I said I'm interested in something that I will call a Bivector field. Let me say what this means for the surface, like how I can obtain such a thing. So in particular, my surface topologically, they're just wedges of circles, so they're k pi 1s, so I can compute group homology, or like either homology of surface or take group homology. So I can just identify this. This is also sort of where this weird reduced thing comes from, because I want to take reduced homology on the topological side. But it comes with some local system, and the local system is described as follows. So I mean, the local system was here, so like with left and right action, and one description of that would be, so over a point on the surface, it assigns sort of the k linear combinations of paths between them, or sort of homotopy class of paths.
What's the symbol between the signals? When you say
Smash. This is smash. I could also stop at this point and refer to your talk, because we already have an element in here if this was a manifold. This was like this equivalent intersection pairing that was introduced. There is some canonical element in here. Let me maybe still say like how it will arise here, like one way how it can arise. There's some kind of slight thing that, so we want to do the following thing. I want to take everything relative to the complement of the diagonal. That's usually how one does geometric intersections. And there's sort of like one slight annoying thing that these guys to intersect a diagonal, so I need to separate them. Or so I could. Let me see what the solution is. The solution is we need to like move one of those slightly to the left, say. So let's also choose moving left, and the left makes sense because the circle will be oriented and the points are on the boundary, so I can move them slightly to one side. And I will obtain a different pair, like sort of slightly different points, but I sort of need to remember how I moved them. So doing the same move here will allow me to change one of them to pluses, and then I can also remove here without changing anything after homotopy. So then afterwards everything will lie off of the diagonal, and I can do this thing. So this guy now, so using a dual neighborhood, this will be the same thing as the tangent bundle and tangent bundle minus the zero section, or the homology of the tone space. That's why here, and this guy, so like before this local system, like there's no sort of, it doesn't make make sense to restrict it, let's say, just to k. Like it doesn't, it neither maps, I guess it maps to k, but at least like on this guy, since we're now only on the diagonal, this is the same as the joint representation, so it just splits into conjugacy classes. So inside here, I can just pick out, let's say, just k. And now here I can take a Tom class. As well, I'm claiming, so I already have like some canonical bivector field that the goal will be then to lift. And maybe just mention that there is a formula for this bivector field. For now, I'll sort of finally choose generators. But sort of in such a good way that so that they're all embedded. The pairwise don't intersect, and also like this is because I did this move from like pluses to minus, they just started. Let me call this. This is due to fucking Rosley. I have generators for this, so I also have generators, like generators for this I, which also gives me generators for I dual, which I denote by these partials. And then I claim that the formula will look something like, so at each vertex you look at all the paths that end at that vertex. Ending or starting. At that vertex, and moreover, because we're like, sort of, they're all embedded, or sort of as embedded like, as they could be. So like whenever they start, like we can order them linearly. So let's also linearly order them. And the formula would just be something like that. Or maybe I should say those inverses. And the inverse I, you could say, it's given by the same construction where inverse rotation of one of those. But there's just a formula for this. Sort of multiply one of those guys by the corresponding element. And so in particular, like there's no, like if you write like that, there's sort of no coefficient in front. I mean, like there would be if we wrote it in slightly different way. And so now finally, let me also say what would have changed here. So we said we don't, the thing I just erased, so we didn't want an element here, but we actually wanted something relative to this thing. So we wanted to lift this to something that actually relative to the diagonal. Now if I go through this sort of Tom construction, and what I end up here is, so I should maybe remove a little bit more of the diagonal, then it should also be relative to the zero section. So I need to lift my element to here. And it turns out whether this is the Tom class, and I'm asking, it's not supposed to intersect the zero section, but Tom class on the zero section is the Euler class. So in particular, I need to trivialize the Euler class, which is same as choosing a non-vanishing vector field. So in particular, if I have a non-vanishing vector field, then I can sort of do this using some vector field. So there is this lift, and I can do this construction. Maybe
Florian, I just had a question. Maybe I missed this. At some point you mentioned that the intersection form. So you're trying to compute the intersection form here? Or what's the...
yeah. I want to make so. I have this I have this intersection form. Yeah, and like if you choose some kind of coordinates, then you can write down a formula for it. Now I want to lift it. So the intersection form. In particular, you can restrict it to the diagonal. So you can just intersect things with themselves. So that's the same as like sort of multiplying with the Euler class. And I want to lift this class to something that's zero on the diagonal. I want to lift the intersection form to a homology class in here. And the claim is there's two ways how I can do this. So there's like a very geometric way where I go through exactly the same thing here. Then I see in the end so I have some Tom class and I need to make it sort of zero on the zero section. And I can do that if I choose a vector field. But like sort of in the first part is that there's a completely different way how, like a purely algebraic way how I can produce this relative lift. And I said there it's actually, so it's enough to sort of trivialize some sort of class in K theory. I think I said like just two ways I can write this, either geometry or using sort of simple homotopy theory. But the proposition is that those are, or like the theorem is that those two things are actually the same in the end. Does that answer your question? Or
Kind of, I might ask you a bit more.
so maybe just like one small thing, so like an element in here, I can just, or I can think of it in the following way. So it gives me the following. So if I have a path in the surface, I can construct the following two simplex. By just evaluating the path at 2 points. So let's call these two simplex B of gamma. So the boundary of that two simplex is, right, so either if those two things, the parameters are the same, or if one of them is at the boundary. So if they're at the boundary, then I'm zero anyways. So the only boundary of that two simplex lies actually on the diagonal. And sort of like the pair of this guy and that guy gives me the homology class and I could have lifted it just as well. No difference. So in particular, I get an element in. Here, then, so these guys I can evaluate against, or cap against this class here. And the claim is if you do this capping, then you end up with an element just in K pi, and the claim is this is a version of Turaev's loop operator. And they're capping this with the lift of this intersection pairing. This is computed as follows. So what you do is we have our loop, and at each double point we can write it as like three things. And what the loop operation will do is just kill the middle guy and concatenate the rest. Schematically. This thing. So I'm checking like some very geometric things. And so like so what I mentioned before is that so now those two constructions they give us the same. Right, so there's either I can have like this NC volume form plus the non-relative intersection pairing. This gives me a life using this complicated formula from the first part. Or also this like made relative right here. Technically we use a framing. And H coincides, and this is the end of my.
Okay, well, thanks a lot. I had some question about the blackboard which is now covered, this D-1. I got it got erased, but there was a formula that D-1 is gamma -1 D, something like that.
D minus 1.
Or D minus, or I forgot. D minus was gamma. Yeah. Yes. So I again find it slightly confusing with gamma -1. Should I think about it as an adjoint action?
Yeah. I mean, more adjoint than just like left, right? Or
So whenever you write adjoint, it's actually left, and whenever you write left, it's actually adjoint.
right, sort of like the problem, or like whenever something was in the Lie algebra or in the Lie algebra rule, there is no left or right action, so there's only one action, and it's the same, or like it's the same action as like the one on all these things. So yeah, I could have written them as a joint here, which would have made it confusing in a different way.
Yeah. So this is an action similar to the action on those dxx -1.
Yeah.
I'm curious why you when you write the formula for the Fox derivative, and you said that if you write in the symbols of the differential, it makes the formula more natural. The Fox, natural in what sense? I mean, it will become some just Leibniz rules or something. For
The calculation that I think I have to find. It's just nothing, Alex, just if you do the calculation here, then you exactly would just end up with the inverse. And if we now use the rule from just before that, we don't write adjoints, we just write them like this. I guess here I should. So if I do it like this, then there's sort of like, yeah, it doesn't look so confusing, and this Fox tree, at least they look a bit, or like, maybe not unnatural, but at least maybe not very symmetric.
More questions? Okay, well, if not, thanks again.